In this lesson, we'll explore a few cool features you can implement on your switch ports that can help with monitoring and security. Let's start with port mirroring. Port mirroring is a switch configuration that's used to monitor network traffic. A copy of all network packets from a selected port is copied and sent to another port for analysis. The selected port could include an entire VLAN. This is typically used for security, diagnosing errors, or monitoring things like intrusion detection systems, application performance, and VoIP calls. The activity usually goes unseen by other network devices. Port mirroring has different names depending on the switch you have. For example, port mirroring on a Cisco switch is called Switch Port Analyzer, or SPAN. On 3Com networks, it's called Roving Analysis Port, or RAP. Another feature switch ports offer is a configuration called port security. Because switch ports are open to traffic by default, they're some of the most vulnerable devices on a network. Port security provides protection by allowing you to limit the number of MAC addresses that can be added to a switch's MAC address table. You can configure your switch to build its MAC address table dynamically, statically, or both. With dynamic locking, a sticky feature is used to automatically add MAC addresses to the table. MAC addresses are added until the table's capacity is reached. With static locking, each MAC address is manually added to the table. A MAC address entry that was dynamically added will drop from the table if it hasn't been used in a specified amount of time. But any manually added MAC addresses are static and won't time out. To use both static and dynamic locking, you can manually add some MAC addresses to the table and then use the sticky feature to dynamically add any incoming traffic's MAC addresses. These can be added until the capacity has been reached. Violations occur when traffic comes to a secure switch from devices that aren't listed in the table or when the table's capacity is full. You can choose which action should be taken in the event of a port security violation. There are 3 mode options to choose from: protect, restrict, or shut down. You can only use protect mode with the sticky feature. When a violation occurs in this mode, the frames are dropped. The interface still functions, but no log entries are made. Restrict mode drops frames in the event of a violation as well, and the interface still continues to function. In addition, the switch logs the violation and sends a security violation alert. Shutdown mode disables the port and sends a security violation alert. This is the default violation mode, and the port can only function again when you manually configure a no shutdown command. Another feature that can help simplify your network is Power over Ethernet, or PoE, which refers to an Ethernet cable that provides electrical power to a device as well as data. This eliminates the need to have a separate AC/DC power supply or a nearby outlet for the connected device. Using PoE, you can extend your network without adding additional electrical outlets. There are many devices that are PoE compatible, like VoIP phones, IP security cameras, and network repeaters. Some switches also have PoE capabilities, and the nice thing about these switches is that they can provide power to other PoE devices they connect to, as long as the devices require 15.4 watts or less of power. PoE is great for low-watt devices, and there was a time that was all that was needed. But as technology improved, more and more devices were created that required more watts. So, in 2009, a new standard was added called Power over Ethernet Plus, or PoE Plus. PoE Plus provides up to 25.5 watts of power. This can support devices like PTZ cameras, alarm systems, and video phones. In 2018, the Institute of Electrical and Electronics Engineers, or IEEE, introduced a new standard that included 2 more power types for PoE. These were Type 3, which delivers up to 51 watts, and Type 4, which delivers up to 71.3 watts. These are referred to as PoE++ Type 3 and PoE++ Type 4. Type 3 powers devices like video conferencing equipment, surveillance cameras, and multi-radio wireless access points. Type 4 can power devices such as flat screens, laptops, and even digital signage. If your switch doesn't support PoE, you can add an injector between it and the device. Many switches include powered and non-powered ports. It's good to have the option because it can cause damage to connect a non-PoE device to a powered port. There are some switches available that are even more intelligent and can automatically sense if the connected device is a PoE device or not and turn off power when not needed. Overall, PoE switches can be beneficial by saving you from extra wiring, allowing remote monitoring and control, and extending your network. One downside to them is that if you lose power to the switch, everything connected to it loses power too. So just keep that in mind when you're setting up your network. An important component to keeping your network up and running is having redundancies in your connections so that if one goes down, the network can continue without interruption. The danger of redundancy is that it can create a switching loop. Let's look at how this happens. In this diagram, we have a couple of switches with endpoints connected. It's important to realize that if a broadcast frame is sent from this workstation on switch A to the local switch port, switch A is going to copy that frame to all its other ports. The frame gets copied to the station on top, to the station on bottom, and to the switch next door, switch B. When switch B receives the broadcast frame, it does the same thing. It copies the frame to all connected nodes. It doesn't matter which switch you're connected to. A broadcast frame will propagate to all the switches it can reach. This is normal behavior and how things are supposed to work. But let's look at what happens if we add a second link between these switches. As we saw before, the workstation on switch A sends a broadcast frame to the local switch, and it's copied to all other ports, including the ports that lead to switch B. Switch B receives the frame, copies it to the workstations, and copies it to the other port on that switch, which leads back to switch A. That broadcast frame actually makes a loop here and ends up right back on the segment leading to switch A. The same thing would happen to the signal coming in from the bottom. It would loop through switch B and back to switch A. This is basically what a switching loop is. It's bad because data is now circling around the network as fast as the switches can process the frames. This is the beginning of what's called a broadcast storm, and it can take down your network very quickly. So how do we solve this problem? We do it with Spanning Tree Protocol, or STP. This protocol assigns one bridge for each route as the designated bridge. Only the designated bridge can forward packets, and redundant bridges are assigned as backups. Having just one active bridge makes switching loops impossible, as there's not a loop for them to travel anymore. STP also provides redundant paths between devices, enables dynamic role configuration, helps the network recover automatically from a topology change or device failure, and identifies the optimal path between any two network devices. These important functions are why it's enabled by default on many devices. STP works using three things: bridge roles, port states, and port types. We won't discuss those in detail here, but let's look at how they work to stop switching loops from happening. Let's go back to our switches connected with redundant links. Let's say switch A's bridge ID is 1 and switch B's is 2. These aren't what bridge IDs look like. They're usually several bytes in length, but we're going to use 1 and 2 here for simplicity. STP sends Bridge Protocol Data Units, or BPDUs, out each connected port when the switches come up. The BPDUs carry the bridge ID within them to alert the switch next door of what's connected to it. Switch B does the same thing and sends BPDUs out to all connected ports to look for neighboring switches. Switch B will see BPDUs coming in from switch A over both these connections. Because switch A has a lower bridge ID, which represents a higher priority to STP, it'll have the first chance at taking responsibility for segments. There's only one way to block the loop in the middle. You must sever one of the connections. One of the ports on switch A or switch B has to be put into a blocked state to effectively sever the loop. Because switch A is the dominant switch in this case, it'll remain active on both its ports. These two ports will remain in a forwarding state on switch A. The connection with the lowest port number on switch B, let's say that's the bottom port, will be active between the two switches. But on switch B, the other side of this top link will be in a blocked state. What you end up with is one connection between switch A and switch B, which is this bottom connection. No data traverses the top connection between the two switches, and this eliminates the loop. If the bottom link goes down sometime, this top link is still active. It's still physically connected to the two switches. STP would realize that there's no longer an active connection between the switches and unblock this port so that the top connection becomes active again. That's it for this lesson. In this lesson, we talked about port mirroring, which gives you as a network administrator the ability to monitor your switches for performance and security. Then we discussed how port security helps you guard your switch ports and the violation settings you can choose from if your parameters are broken. Next, we went over PoE switches and devices, and last of all, we looked at spanning tree protocol and how it can eliminate loops and broadcast storms while still allowing you to have redundancy on your switches.